Okay, can we start? Hi, I'm Andrei Bauer, in case you don't know, and this is the course on formalized mathematics and proof assistance, which is going to, which also allows master students to show up. How many master students do we have? 1, 2, 3, 4, 5, 6, 7, 7, and we have 1, 2 doctoral students. Okay, so the course is for you and they're just guests. Yes. Okay, and we have Daniel there. And now we have even more master students. Welcome. Okay, so in this course, we are going to learn about formalized math, which is mathematics done with computers, with programs called proof assistants that verify all steps of all your constructions and proofs. And this is a topic that has been developed for decades. It started, the first ones were in the 60s, but it really kind of took off starting in the 90s. And there is a lot of experience built into proof assistants. And it's until recently, this was mostly a topic in computer science because they were used, and still are used for software verification and protocol verification. So verification of various parts of things that happen in computer science. But we are going to focus on formalization of mathematics. And we're going to use the proof assistant Lean because it has recently taken the math community it's becoming very popular. And so I think it's most sensible to just use Lean at this point. And the idea is that we try to explain not only how to formalize math, which is sort of a craft on its own, but also how proof assistants work so that you have some idea of what's happening inside the proof assistant so that your brain doesn't have to build a random model of what's going on. So I will explain in lectures. Often I will explain sort of the background of what's going on, but for the course itself, to pass the course, you have to complete a small formalization project. And since your number is fairly bounded, I think we can have personal formalization projects. If it turns out that there's 50 of you, then we would start forming teams because it would be beyond my capacity to oversee 50 projects. But with this number, I think you can have individual projects. However, if there are people who would like to cooperate and have a larger project, please talk to me. The thing that needs to be clear is who's doing what, so that you know what your part of the project is. But we can also have sort of combined projects, which maybe accomplish something more ambitious. The lectures are Fridays, 10 to 12, just like this one. In here, I am recording all the lectures and I'll put them up on YouTube. So in case you miss a lecture, you can still watch it later. Regarding other logistics, there is going to be if you go to, well, their starting point should be Spletna Učilnica, which has the course. No, invalid. How is this now suddenly invalid? We still have the slowest login of all Spletna Učilnica. So here, when you enter for the first time, it asks you to enroll. Let's see if everybody's here. Okay, Luca. No, there will be lots. Okay, so this is going to be a superset of people who are actually present. Imane, do we have this person? No. Okay, we have Kerem. That's him. Okay, Leonard. We don't have Leonard. Philip. We don't. Luca. There. Jure. Okay. Jon. Yeah, over there. Mateusz. Timon. Well, okay. Maribel. Okay. Urban. Job. Okay, no, I know he's not here. Tomasz. Daniel is over there. Jure is over here. Luna is over here. So we are missing the doctoral students. And okay, I believe you have enough experience to put yourself on this list. The doctoral students, we can do that later, okay? But this is in case I need to like send out an announcement. But what I would really prefer is if we can use Discord for the course. And so the Discord stuff is on the departmental Discord server, which has all the other courses. So you go in, you download the updates. It always, what? I mean, they have like an update every 5 hours on Discord. Yes, of course, sure. Now everybody knows how many characters I have in my local password. And everybody knows that it's not sufficiently many. Okay, while Discord is finding its way around, you have some basic, you have some basic resources here on Split Now Chilnica where you can ask things like the Proof Assistance Stack Exchange site, the Lean Prover Zulip, that's also a chat system, is also very, okay, so you go here. This is the ULFMF, and then when you get in, under here, you find the course somewhere, FFF, this one, format, and then you subscribe, and then it's going to show up. And then I would like everybody who comes in, once you're successfully in Discord here, hey, say hi. And you should say also who you are in case your username is something like teapot, you know, or not recognizable and actually identifiable. Just say, I'm such and such. There we go. You see, here's a person. These are all people with normal usernames. Okay. This is going to be useful because when you are actually trying to formalize things, it'll be like learning how to ride a bike. And it will be very helpful to have people who hold your balance a little bit. And so just ask on Discord. I know we have some people present who have ample experience with proof assistance, so they will be able to help, but I will also try to help. And so I hope we can use Discord for useful communication. Okay, I think that's about it right now for the logistics. Let's talk about what this course is about. Okay, so first of all, I failed to put in a link. There's a link to something. I'll put the link in. I'm going to have sort of a little bit, I'm preparing lecture notes, and anything that I write here in the classroom will be uploaded also as PDFs. These lecture notes are not going to be an entire textbook because there are so many resources available for Lean and for type theory and for everything that this is going to be more of an outline of what we're doing, and I will be referring to external resources. So for instance, for today's lecture on type theory, there's a reading material down here. You have Egbert's book. It's called Introduction to Homotopy Type Theory, but don't worry, there is no homotopy in chapters 1 to 4. It's just type theory. So that's a good textbook that can serve as an introduction to type theory. And if you are more interested in particular what the type theory of Lean looks like, you can look at master's thesis of Mario Carneros, which is some PDF that is going to be probably a little bit, that's his master's thesis, which explains in a more formal way the exact rules. So some people like exact rules, okay? In case you want to read this stuff. Whereas Egbert's textbook is really meant as a learning resource where you start to learn type theory from scratch. What I'm going to do in today's lecture is we're going to explain things about type theory. If you look ahead, there is a second lecture which is called the Lean Installation Party, but this is not going to be a real lecture. This is more like your homework for the next week, which is you should get a working installation of Lean going somewhere. So is it safe to assume that everybody has access to a computer in this classroom? Okay, if you don't have a computer at all, let us know. We'll try to get you one. Okay, so you should have a computer. You should Lean works, the resources, the Visual Studio Code and Lean work on Mac OS, Windows, and Linux. So if you're using an operating system that is not one of those three, please come talk to me. I'll take a photo of you. So you have fairly good instructions on how to get Lean installed. And actually the first step is you get Visual Studio Code installed. That's an editor. And then Lean can be installed. Well, just follow the instructions. Lean has fairly good user support. And you will also have to know about Git. Okay. Who has used Git before? Hands up. Okay. So good. Excellent. Very good to know. Still, Git is complicated, as we all know. That's why we have Discord. So when you do some horrible thing with your Git, ask on Discord. Say, I'm sorry, I did a horrible thing. I Googled, I still cannot solve it. And what do I do next? It would be ideal if you can, by the next lecture, everybody can get Lean working using the instructions on your computer. And when you do so, that's your second job for this Discord. Say, hi, I have a working Lean. Okay, so there we go. Okay, so just so that I see that things are happening. Okay, so that I can tell that people are actually did something, and that I can next time maybe assume that if I say try this thing in Lean, you will actually be able to try that thing in Lean. Okay, so enough about logistics. Let's talk about today's lecture. So today's lecture is going to be about type theory. Type theory is a formalism. Let's see if I still remember how to use this. Type theory. It's a formalism that is used in proof assistance. It's different from set theory, which most mathematicians are familiar with as a foundation of mathematics. You're quite familiar with sets and you work with sets. But the way formal set theory is usually done is not quite the right way for implementation in a proof assistant. So proof assistants use this other formalism. There's another, so there are two, I would say there are two main reasons why we want to use type theory. The first one is that as a formalism, type theory is much closer to how you actually work in mathematical practice. You say that you use sets, but you actually do something that's closer to type theory. So that's why proof assistants that's one reason why proof assistants use type theory. Another one is that you can use type theory simultaneously as a foundation of mathematics and a programming language. And that is a very nice combination to have when you are in a proof assistant and you need to also not just write down theorems, but also perform computations. And so that's another reason. So we're going to look at type theory. Now, there are many ways to introduce type theory, some more mysterious than others. And the least mysterious way for me to introduce type theory is to just slightly lie to you and say that type theory is just set theory, but done with a different set, with a different collection of primitives. So for the purposes of this lecture, and for a little while, at least in this course, a type is just a set. Okay, so don't worry about anything. There are people in here who know how the types are not sets. You can talk to them. Good luck trying to understand what they're saying. But for now, just types are sets. Okay? Completely, nothing is happening. So my goal for today is to trick you into thinking that type theory is easy by saying that it is set theory. So once we actually encounter differences, then we'll discuss them. But in the beginning, there is no difference. So you can just say type is a set. Okay? And I will use them as synonyms. There will be one other change, immediate change, which is in type theory, we write elementhood when we write E. I see this notepad is going to present problems to me. This elementhood will be written as like this: A colon A, E colon A, instead of element of. Again, there are slight formal differences between these two notions, but this is not something that we should worry about in the first lecture on type theory. Now, usually, set theory has a certain collection of axioms which are mostly about the fact that certain kinds of sets exist. We are going to, in type theory, we start slightly differently. We take a different collection of primitives than you would in set theory. So what are the basic primitives in set theory? Well, the basic primitives in set theory would be things like if we go just down the list of the axioms and say, well, the axioms introduce certain constructions, what are they? Well, there's an axiom that gives you the empty set, then there are unordered pairs, then there are unions, then there are subsets, power sets, right? You can get intersections using subsets. So X in A. So there is a certain collection of constructions that one uses that gets set theory going. We are going to use a different collection. It's going to be just an alternative set that emphasizes other constructions, not the ones up here. These are constructions that are much closer to how things are done in programming languages, and but they still try to capture the kind of moves that you do when you work in mathematics. So there's going to be that's the main difference, is that it's a different choice. You can encode you can encode one with the other. It goes in both directions. So okay, so there's also a second kind of important change, which is the change in methodology. So if you look at how set theory is set up, it's got axioms, and these axioms introduce the above constructions not by naming them, but rather these axioms always say that a certain kind of set exists. So for instance, if we look at the power set axiom, the power set axiom says the following. It says, for every set, okay, I'll write it down with a scary formula, but if I read it, it's not going to be scary. Okay, for every set A, there exists a set P, such that for every set B, B is in P, if and only if B is a subset of A. Where B is a subset of A is a further abbreviation, because you could write this as for all X in B, X is in A, right? So that's an axiom. It's a for all exists for all, so okay, but you never work like this. I mean, you don't actually say these things when you work with sets. What you do instead, you immediately introduce an operation, which you call the power set of operation. So you say the power set of A, and you call it. Okay, so that's a new operation that forms sets. And then once you say, okay, we have an operation, if I just say there is an operation, then that doesn't actually say anything. It doesn't say much, at least. So we also need to characterize what this operation does. Now we could just this axiom up here, we could just rephrase it using the P of A. So then instead of for all A exists P, we will just use the operation. So then there will be also a way of saying what this does, which is that for all B, B is an element of P of A, if and only if B is a subset of A. Now, if you do algebra, you would say, from the point of view of algebra, having an operation is a good thing. In algebra, we really, really like operations, plus, minus, times, power set, so that's good. This is less good because it's not an equation. In algebra, we really prefer equations. So we would want a way of turning this into an equation. And I'm not going to go into how this is done. It can be done. Okay. You would need another operation. So maybe I can say a little bit. You would need another operation which helps you actually create some elements of P of A. Because right now, what the elements of P of A are is prescribed by this axiom, which is saying among all the things that exist in this wide universe of mathematical objects, these are the elements of P of A. Well, that's not how you do algebra. When you describe natural numbers, you don't say, among all things in mathematics, some of them we will characterize as being numbers. Actually, we do that. Well, those were early attempts at natural numbers, right? So the natural number 3 is the set of all things that have 3 elements, but you have to say it in a non-cyclic way. So anyhow, instead, what we want is we want further operations that will generate elements of P of A. So how do you generate it? What is the operation that generates an element of P of A? Well, what are the elements of P of A? They are the subsets. Is there a known operation that forms subset? Sure, it's written like this. So you would want to have another operation. Right? And this one would land in P of A then. And this is now, we have two operations, the power set operation and the subset operation. You see that this subset operation is kind of fancy, right? It's not as easy as just successor for natural numbers because it's complicated in its form. And now you would be on your way to be able to maybe explain a little bit about how, write down some equations. So the idea is going to be that in type theory, for me, one of the useful views of type theory is that it is just a very fancy form of algebra. It's complicated in a certain direction. It emphasizes a certain possible direction of developing algebra that is not common to classical algebraic thinking of, when you have rings and modules, you're sort of going in a different direction. So here we're going to make algebra that is super expressive. It's going to be so expressive that we will be able to just express all of mathematics in it. So it's about that. But the method of type theory is essentially algebraic. So in type theory, we just like in set theory, we really like operations, but we call them also constructions or constructions. And these come at all levels. There will be constructions that make new sets or new types, and there will be constructions that make elements of types or elements of sets. So let's take, again, an algebraic point of view. You have something like addition in a ring. Well, that's a way of creating elements in a ring. It's an operation in a ring. But you also have operations on rings, like the Cartesian product of two rings, or some direct limit of rings, or things like that, or a quotient ring. Those are also operations, but they act on a higher level. They act on rings. Nevertheless, they are operations. And so this is very much how we want to do things, with operations / constructions, because you usually call them constructions when they're on this high level. Okay? And then we want axioms. If you just say there are operations, there's nothing else then then it's worse than just having Lego blocks, right? So Lego blocks are like ways of making constructions. You have some basic building blocks and you can make constructions. But Lego blocks are more than that. Lego blocks satisfy certain algebraic laws. For instance, if I have a Lego block, I can from my Legos, I can first build the walls of a house and then the roof and put it on top. Or I can first build the roof and then I build the walls and put them together. So that's a kind of commutativity or associativity law. So the Lego, if you think about it, the Lego blocks satisfy certain equations. So, putting a Lego block on top and then another one on bottom is the same as first putting the one on bottom and then the one on top. There are equations. So we want equations. So the other thing that we really, really like is equations. If we compare this to set theory, you see a certain difference. Set theory has no problem with complicated logical statements. Set theory thrives on logic. It wants to use logical statements to make a point. Algebra wants to build and construct things, and it wants to study how they relate by observing which things are equal. This approach we like, again, now for several reasons. First, it is going to allow us to speak about constructions in a very simple way because they will be just built in. And a lot of mathematics is about constructions. And we prefer equations because it is easier to compute with equations than with arbitrary logical statements. There's very little you can do about for all exists for all. That's super complicated. You might do theorem proving or whatnot, but equations, if you have good algorithms for checking equations, that is going to be quite helpful because then your tool, your proof assistant, will be able to help you with the laws. It'll be able to verify that laws hold when they're supposed to hold by running certain algorithms. Now, it's not going to be perfect because, as we well know, we can arrange in algebra and elsewhere for such equations to be very, very complicated. They can be undecidable, so there's no algorithm to decide them. So in general, you should expect that the proof assistant, up to a point, will be able to do things by itself because it's got built-in algorithms. But after that, it will want your help. So if you're doing something with equations that requires an induction proof, such as commutativity of addition of natural numbers, then you will have to do the induction proof. But if it's something fairly trivial that can be resolved algorithmically, such as, oh, we just unfolded the definition and then we applied this function to this argument, we put the argument in, and then we simplify it a little further, that's the kind of thing that will be done automatically. Okay, so what does now this type theory look like or set theory, our foundation, where we say, let's just do operations and constructions and equations and nothing else. Okay, so I should be able to have an example. So let's have an example of that. And the example, which I think works nicely at the beginning, is Cartesian product. So binary product. There will be two levels of operations / constructions. So first of all, I will generally call it a construction when it's just at the level of types or sets, and I will call it an operation when it creates elements of sets. This at some point will be blurred because we're going to introduce types of types, and then it gets mixed up. But so we want to have a basic construction. Now, how are we going to write things? There will be a specific way of writing things that will also make it easier for you to read type theoretic literature or anybody giving you rules. And the way you do this is you write down these fractions. So you should try this in your paper. Like if you make a wiggly line and you just hold, does it become straight? Okay, so here we go. So you make a construction or any kind of thing that I will be writing down. This is going to be what is called an inference rule. Okay, so when you have an inference rule, you put your premises, so requirements, on top, and then whatever is the conclusion, you put it on the bottom. So here I would say something like this. If A is a set, and you should be jumping up and down at this moment. Oh, okay, so let's do some renaming here. Okay, so we said we're going to write things. So I might write this, but actually I will write that. We are immediately hitting certain foundational issues, like, am I saying that there is a set of all sets? Well, right now I am making it a little bit fuzzy. As we all know, there is no set of all sets. You can think of this as the class of all sets, because this is what you were told in school, that you have to be careful about the set of all sets. And then somebody introduced another word for set and said, now it's okay. So this is the class of all sets. So this would be the type of all types. Not really. We will see later on that we actually have a hierarchy of types, and you can think of set and class as just the first step of this hierarchy. In Lean, this hierarchy goes much higher. It goes infinitely high. And there is a very practical reason for that you need all of them. It's not a philosophical commitment to having an even larger universe. So if I write A colon type, that just means A is a type. And right now, we're not going to worry about whether this is the type of all types or whether this is what this is. Just we are still working fairly naively, trying to explain ideas. Okay, so if A is a type and B is a type, you see now I have two premises, then I say A cross B is a type. This is how a type theorist would say there is an operation cross, which is a binary operation. That's what it is. We didn't actually say what this does. For all we know, A cross B could always be the natural numbers or something strange. We do not yet know what this is. We just know that there is a construction. So the next thing that you need to do, you need to explain, okay, what is this set or type? And the way you explain what this type is that you give two kinds of constructions. You give constructions or operations, pardon me. You give two kinds of operations. Operations that create elements of this set. And then you give operations which do something with the elements of this set. Because if you only ever create elements, but you have no ability to actually do anything with them, then that's not going to be terribly useful. And if you have no way of creating them, then that's not going to be terribly useful either. So we want to have some operations. Okay, so what are the operations? Pairing will be the first one. So how does pairing go? It goes like this. If A, I don't know what, if A is an element of A and B is an element of B, then we want to say there is an operation here. And now we get into notational things. Like, for instance, here I wrote times. So I allow myself to introduce suggestive traditional notations, right? A more formalist way of writing this, if this was 1985 and the only characters that existed on the computer were ASCII code, then once we get to formalization, we would have a hard time writing down times. So we would actually be writing something like prod A, B, or some strange thing like that. And then here we would have to write something like pair A, B. This is the kind of formalism that would only be relevant if this were some sort of a course where we emphasized the formal aspects of type theory, which we are not. Luckily, because it's not 1985, there are UTF-8 characters, and so we can use these normal notations, and Lean does, and modern proof assistants do, so we can do that. Okay, so we have an operation that creates an element of this set. What would be an operation that takes it apart? So that would be something like this. If I have an element, let's call it U, of A cross B, how do I get to it? How do I do anything with it? Well, there are two things you can do. You expect, the idea, of course, is that you are able to actually tell what the first and the second components are, which, by the way, is different from other binary operations that you might see in algebra. When I add two numbers, I do not expect to be able to recover the numbers that I added. But here I do. So I give myself an operation that does that. So let's call it pi. So I can say there's an operation called pi1 that's going to give me A. So these are projections. And then, of course, there's going to be another one, which is pi2, and the mighty computational power of this laptop and is not sufficient to track my pen, it seems. Pi2 of U, and that's going to give you B. So now I have two further. So now I have one construction and three operations. We're not done, because right now I have no idea what this is and what it does. I need something else. I need equations. So I need equations which explain these equations. Always the methodology that we follow here in type 2 is you always explain what happens if you put something together and then you take it apart immediately. And the other way around, you have something, you take it apart, you put it back together, what happens? So by the way, sometimes what taking apart means is not so easy to determine, but here will be the equations. So I put something together and I immediately take it apart. What happens? It's, you get A. Is there another one? Yes, there's another way of taking apart. Pi2 of AB is B. There's another one. If I have a U, I can take it apart. How do I put it back together? Well, I also need the other part. And then I put them together. What will I get? U. Okay. These equations and constructions are now sufficient to determine A cross B up to isomorphism. So if once you start interpreting these things in categories, you see that these are precisely the universal properties of a binary product in a category. Where are they? Well, let's see. It's a construction. We have two projections. The two triangles commute. And this, you have to think about this. This is what gives you the universal property, the uniqueness of the universal property. So, that's pretty nice. Okay? And this is the method. Always this method. So let's do one more. The next one is interesting for a simple reason that only programmers are told about it, but mathematicians are not told about it. And the reason they're not told about it is because classical set theory emphasizes unions instead of disjoint unions. But disjoint unions are just as fundamental as unions. Just because you can encode disjoint unions using unions and Cartesian products, that doesn't mean they're less fundamental. When you have a lot of these fundamental principles can be encoded with each other. And so, that's not really a good measure. The reason why disjoint union, or what we're going to call it a binary sum, is fundamental is because this is what is a coproduct in a category. So let's do binary sum. Okay, so we have one construction. If I have a type A, I have a type B, then I can get a type which I will just simply call A plus B. Okay, what are the operations? How do I create elements of A plus B? Well, if I have an element in A, then I can inject A into A plus B, and I'm going to write this as iota 1 for injection or inclusion, and that will give me an element A plus B. So this iota 1 is a primitive symbol, just like this pi 1 was a primitive symbol up here. And then there is another one, B in B. This is iota 2 of B, A plus B. Oh, quiz question. People sometimes think that it would be a good idea to write instead of iota 1, iota A. And instead of writing pi 1, they want to write pi A. Why is this a bad idea? Why is this an exquisitely bad idea? It's an awful idea. Yes? Because what will, well, yeah, I think you're saying the same thing. But what if you do that and you write this one as iota of B, okay? What will happen when you form the coproduct or the sum C plus C? You're going to end up calling both of them iota C. That's not so good, okay? And the same for projections. So this should not be done, yes?
Strictly speaking, the rule will not require to state that B is a type. A is of type A, B should be a type.
Where are we? This, which of the rules? Second, this one.
Okay. Then.
Or here, are you asking why didn't we state that B is a type?
No, in that case, A.
Oh, in that case, A. Yes. Okay, so that is a good question. So here, A just appeared out of thin air, right? So because it appeared out of thin air, you should worry that somebody is going to put a banana in here, okay, instead of a type. So yes, it would be much better to say that you need a type here. Actually, B appeared out of thin air, didn't it? So actually, I should say B is a type.
Would you write the table to type B above B?
Yeah, now maybe because we are in Europe and we read things from left to right, it would be more polite to write B as a type before it. Yeah, okay. But you definitely have a very good point there. And this point leads to the question of how precise do we have to be? Now, the answer is when you're implementing the kernel of a proof assistant, you have to be 100% precise. The computer is completely unforgiving. When you're a human, you cannot deal with this. It's too much. This formalism will kill your brain. So when you're a human, you want to be sloppy. When you're a computer, you by design you're not sloppy. So we are going to, this is actually a very, very important issue in formalization of mathematics, because it means that a human who is communicating with a computer or another human says things in sloppy ways, yet the other human or the computer is supposed to understand what's going on. Our entire second lecture is devoted just to this point, and it's called invisible mathematics. We will get to it. But right now, to answer a question, is the following. I am presenting these rules the way that I would present them to a human, and I want to make the point that there are operations and constructions. If we got more precise, by the way, we would not be done, because here, to make these things useful, you would say things like, but maybe can I have some variables in here? And then you say, okay, but then what do we do with variables? And we need to address that. And so there will be even more stuff appearing. We will get to that eventually, but you have a good point. Yes. There are levels of precision. The most precise one, I can point you to papers. I don't want to do it in the classroom in front of people when I'm just trying to explain the idea of type theory. If we ever end up discussing how formal is formal type theory, then yes, we can. We have had several PhDs on that topic here, and we might have another one soon. So we know a lot about this formalism, but it would obscure matters for today. Okay, happy?
Okay.
Yep. Am I allowed to do things sloppily from now on? Okay, we'll do. But if you think that something is so here's a very important observation. By the way, we will be forced to observe what humans do. No, sorry, I misspoke. What mathematicians do when they do math. Yes? Why? Because we are transporting the mathematical activity into an environment where everything needs to be precise. So we need to be aware of what is going on. One thing that goes on all the time in communication is error correction. I say something sloppy. Now, if we are very much in sync and have similar experiences, then you will understand what I meant and you will error correct in your head. But if you don't have as much experience, or you have a different experience than mine, or maybe you come from a different background, you will be confused. What will you do? You will ask for a clarification, right? That is, the communication goes both ways. And that's actually an interesting point to keep in mind when we start working with proof assistants. Does it go both ways? Yes, it does. Except that it's done in this annoying way where you say something and then instead of the machine saying something back, it complains, right? It just says error, 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 error. So it's not very polite, but it's just a machine, right? So you have to forgive it. But in this, my point also is this: ask questions in these lectures, right? Just like you did. So if you think any of these rules need a little more clarification, say, I need more clarification. Okay, now, okay, we have constructions. How do you deconstruct? How do you do something with an element? If I say I have u in A plus B, by the way, here I have a missing premise A type. Yeah. So if I have something in A plus B, then what? Well, in programming, this is a case statement. It says, well, there are two ways that you could have arisen. You want to say apart, you want to say apart from these two ways, anything that is in the coproduct, in the plus, needs to be either of this form or that form. And this is what this construction will do. It will say it is sufficient to consider those two forms. So here you would write something like this. You would say, let me write it first. I'll write it in a completely computer sciencey way. Case U of, let's do Haskell. If U is of the form U1 of A, then we do something. Let's say then we do a thing called E1. Or if it is of the form B, then we do some E2. But now we have to explain what this E1 and E2 are. So we need more things. This is a case statement. You say, consider U. There are two cases. It's either of the form iota 1 of A, in which case we do E1, or it's of the form iota 2 of B, in which case we do E2. And everything in the end will be of some type, let's call it C. Okay? So now what? Well, we need to take care of this E1. Well, E1 should be of type C. But this isn't quite right, because E1 may refer to this little a. So now we have to do something else. We need to start introducing variables. We say, under the assumption that we have a parameter called a, and this is how I'm going to write it, E1 has type C. Under the assumption that B has type B, E2 has type C. So if both branches have type C, the result will certainly be of type C, because we're going to select one of the branches and we'll get something of type C. But this here needs explanation. So we have just found out that we need to be able to introduce new parameters, because E1 can use the parameter A here. That's the idea. That's how case statements work in programming languages. So what do we do? Well, we wrote something. Okay, so how do we read this? So in general, we might write things like this. We would write x1 is a parameter from the set a1, x2 is a parameter from a2, xn is a parameter from an, then something here, something. The thing that is called here is called sometimes a thesis, the things that you are asserting, some assertion. So it might be an assertion that some element E is of some type B or something like that. This here says what are the currently known parameters or variables. So these are known variables slash also called parameters. And in fact, if you think about mathematical practice, if you're reading a paper and I point, oh, there should be a break. If I point at any place in the text and ask you, what are the parameters at this point? You should be able to say. So at the beginning of the section, they might say, let V be a vector space. And then later on, they will say, oh, consider two numbers X and Y. And you will see exactly how they got introduced. Remember the word introduced. Parameters get introduced. And then they are available. They may not be, they may disappear after a while because you have just like a branch, a sub-branch of a proof. And some parameter is only used in that sub-branch. So here, the parameter A is only used in E1. It's not everywhere. It has a local existence. So this is also called a context. And contexts, if we were quite precise, we would have to write contexts everywhere up here because all of these rules actually allow variables to appear. So to be completely precise with the bookkeeping, we would have to write them there, but we don't. Your hand is up. I declare a break, 15-minute break. So come back sometime between 20 and 25 past. Okay. You had a question? Okay, I'm not breaking. I'm not. Yeah. Yes. So this kind of context is avoided, but I would say, in essence, the same kind of information is provided. Right? So in essence, you still know that whatever you're doing may depend on certain things called parameters, free variables, whatever you want to call them. It's what is accomplished, I think, is pretty much the same. But yes, of course, there will be different formalisms. If you really, really want to avoid variables, you have to stick to something like a combinatory calculus with combinators, a la Schoenfinkel. But that is not something that humans are good at. Okay, let's go on. So I should say that Egbert's book is, I think, a very good introduction to what I'm explaining now. In terms of precision, it is more precise, but it's still not overwhelmingly formal. So I do think that is a suitable reading for this week. As I said earlier, there will be resources that you should be looking at. And if you really want to get a good feel for type theory, read something about type theory. And if you're going to read anything, you could, I think Egbert's book is a good choice. So the introduction, definitely. You are going to learn how to use type theory through the proof assistant. So you don't have to worry about that. But I think it's I know mathematicians have the natural unreasonable tendency to try to understand things. And so, that's something that, so that's why you should read that. Okay, so I'm going to go on now and try to outline what else happens in type theory, but we're not going to have the time to go through all these constructions in equal amount of detail. These two we did in some detail because we still need equations, by the way. We did these in some detail because I wanted to go slow. So in particular, these contexts here, I was just kind of skipping contexts up here. If you are super careful, you would want to always keep track of variables. And of course, the proof assistant will do that for you. Right? Okay, do we have any equations for binary sums? Well, let's follow the strategy. What happens if I create an element of a sum, put it together, and then immediately take it apart. So maybe this was a rather bad choice here of these a's. It would be better if this was x, like that. So, and this one y. So I'm going to write here now x, otherwise I'm going to have a clash. What would you expect happens here? You say, consider iota 1 of a. If it is of the form iota 1 of x, then do this, then this, otherwise that. If it's of the form iota 2 of y, then that. Well, you would expect this to be what? Yes, but not precisely E1, but E1 with... So now we need a notation for substituting, replacing x with a. So I'm going to write it like this. Replace x with a in E1, okay? Books on logic and books on type theory might also write this. And so then it'll take you several years to remember which one goes in and which one goes out because they put in this fraction. This, I think, is more natural, right? Okay, so there's going to be another equation. If we put iota 2 of b here, then here we expect to get E2, but we're going to replace y with b. Is there another one? Well, that one is kind of tricky because you would naively say we take it apart, then we put it back together. So we start with a u, and then we do a case, and then in each case we put it back together. I mean, we can try case u off, and now in each case we put it back together. What does that mean? Well, probably this. So what would you expect to get out of this? Probably a u, right? And this is the equation you actually need to get coproducts, categorical coproducts. But from the point of view of type theory, and certainly from the point of view of algorithmics of type theory, it's not a terribly useful equation because, nobody writes this. It never happens. But it's there. Okay, so what else? Okay, so let's try to explain what happens afterwards. So we have to go back to this idea that things can depend on parameters, on variables, because one of the super important things is that we are going to have dependent types. Which is that since I said that types are sets, this is like saying dependent sets. But what are dependent sets? Well, they're more commonly known as families, okay? Slash families. Let's see how this arises first in practice. So let's first recall, what is a family of sets? Well, a family of sets is a map, which here you have some set that you call the indexing, and then for each index you have a set. So we would write it now like this because we say that type is the same thing as set. What are some examples of this? Suppose you have a text. In the text, this may appear in a slightly different form. Instead of having an explicit family of types, you would have what we would call a dependent type. And this would arise like this. Somebody would just write A, and it would depend on I. And somewhere this I is introduced as a variable. So let me give you an example. So consider the following thing that might appear in a book on algebra. You would say, or maybe not in a book on algebra, on topology. Let n, or no, well, whenever, let n be a natural number, we would say, and then we go blah, 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 and then would say, consider a vector x in R to the n. Let's put this R to the n. Now, this here is a set, but it has this n appearing in it. So n is a parameter. So this is not actually a fixed set. It depends on n. That is the meaning of dependent type. So this is, it depends on n. And this is how you see it in practice. You don't see, nobody ever says in a text, you will never see this. Let us define the map R blank from natural numbers to sets such that n gets mapped to, well, R to the n. Nobody does this family explicitly. It's always done in this implicit way, and then we call it a dependent type. So what are some other examples? Another examples could be somebody says, in the interval n plus 2, there are blah, 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 blah. Here, dependent type. Again, because this is a set, but it depends on n. And this is omnipresent in mathematical arguments. In fact, there are some basic constant types that you usually start with, like natural numbers, real numbers, but the dependent types are probably more common than non-dependent ones. Okay, so this is an important concept, and we are going to do this. We're going to use dependent types all over the place because they are quite natural in mathematical practice. This is all I want to say for now, except that we should look at some operations on dependent types. And there are two basic ones which you should be aware of, which is a product and a sum. So what is the product? This is also called a dependent product. How does it work? Well, given a family of types, we can form, okay, so now we want to say we can form the Cartesian product. Let's try to write it as an inference rule. So as an inference rule, I would write this family in the form of a dependent type like this. So I would say something like this maybe. I would say, suppose I have a type A which depends on I, like this. And when I write this, I mean there could be other variables and other parameters, but I'm just focusing on the fact that there is also a parameter I. There could be some other parameters running around. I'm not saying that there are no others. I'm just displaying the one I'm interested in. And then I say, well, in that case, and now I want to actually, to be a little bit more precise, I want to say that this parameter will disappear. So I say now without the parameter, because I didn't put it here. This is just a funny symbol that logicians really like to use, okay? Which is the turnstile, which is generally used to place on the left of the turnstile, you place hypotheses, parameters, and things like that. And on the other side, you put conclusions or whatever, so the things that you assert. So then we want to say there is a thing called the Cartesian product. And there are many ways of writing Cartesian products, and this might be one of them. Then we can write a type like this. Just a Cartesian product of sets, which I hope you're familiar with. What are its elements? I tuples, right? Or something like that. Well, choice functions, actually. They're functions. So the way that you would introduce another operation, so for creating elements would be like this. You would say, Aha, okay. So suppose that for every I in I can generate some element E of I, which is an element of A of I. Then I can form, and now I want to say I can form a function. Okay, so I will give the type theoretic notation for the function, and then I will give you also a less type theoretic notation. So it would be something like this. E of I is an element of this product. And I really hate my tablet. There we go. And this is just this notation. Normal people would write, again, I say normal people, I mean mathematicians. They would write something like this, maybe mapping I to E of I. But for historic reasons, it's called lambda. And the fault goes with my academic grandfather, Alonzo Church, who thought it was a good idea to use lambda because in those times people really liked Greek letters. And Russell had a iota, Hilbert had an epsilon, and so Church said, I'm going to have a lambda. So lambda, the way you read lambda x dot something means x maps to. So functions. Okay, that's how you make elements. How do you use elements? So if I say, suppose you have an f, which is an element of a Cartesian product, what can you do with it? How do you take apart a function? How do you use a function? You apply it. That's how you use it. So you say, okay, suppose I also have some particular index, let's call it j. Then I can write f of j. And where will I land? In a of j. Yes? What are the equations? Well, put it together. By the way, I will start using abbreviations. I'm not writing the type here, although I should. And this is exactly what's going to happen in a proof assistant. We will, and everywhere else, you start using lots. You start omitting information. So I will pause here to say next week we're going to look at this very carefully. But if you observe what mathematicians do, is they communicate efficiently by telling you as little as possible and expect you to reconstruct the rest. So here you are kind of guessing that very likely this little I ranges over some capital I. And then if I apply that to some j, what do I expect to get? Well, I expect to get E of j. We could write this more formally using substitutions. I was writing E of I here. I could not write this I here. These are formalisms I don't want to get into. Right now, the important thing is there's a thing called Cartesian product or dependent product. It takes a family, creates the product of the family. Okay? It is always useful to look at some special cases. So one possible special case is that you have a product over some indexing set I, but here you always have the same set A. It doesn't vary. What do you get? What kind of functions do you get? Well, from I to A. So this, in fact, is a special case, and we will have a notation for it, which is I to A. So functions, an ordinary function space, an ordinary set of functions from I to A is a special case of a Cartesian product. And this is how a proof assistant will do it as well. This is going to be a special case. Okay. The other operation is a dependent sum. it's a generalization, just like this one was a generalization from a binary product. Oh, by the way, why is this called a product? Let's resolve that. Why is so? This was one special case, is when you have a constant family. But why is this called a product? It better be the case that the binary product is also a product here. Yes. So how do we get the binary product this way? Well, what do we take as an indexing set? Take as the indexing set any set with two elements, say 0 and 1, and then let A0, let that be, say, some set B, and let A1 be some other set C or type. Then when you make this product, then you will get something that is isomorphic to B times C, right? The first component and the second component. So that's why it's called a product. Okay, how about the sum? We have this thing called dependent sum.
Can I just ask?
Yes, of course.
Styles here and before.
Where? Here.
Yeah.
Here I had to use, okay, so I would actually have to use turnstiles all the time to be precise. So, however, if I started writing down turnstiles here 1 hour ago, you would have asked me, what is this? Okay? So I lied to you. This is a time-honored tradition of teaching, is to lie to your students. And so then, here, I used turnstiles whenever there were variables involved. And so when there are variables involved and you want to indicate that some new variable appears locally somewhere, then you need a way of indicating that. And one way to indicate that is to actually say, "Hi, look, we're adding a new variable to our context," and you display it, and it's understood that there could be some other parts of the context somewhere that I'm not showing, because otherwise I would have to say like dot, 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 dot all the time, and I would go crazy. Yes? So I don't do that.
Why is it in the bottom part?
Which one in particular?
I think he means
Oh, in the bottom. Why do I also write it here?
yeah.
To indicate that this variable disappeared. It's not there anymore. This is how I explain that the variable I is bound up here. So here's a trick I do in logic and sets. This thing here, which variables does it have? It's a trick question, so you're supposed to answer, just go for the trick. Which variables does it have?
X and Y.
No, only y. There is no x. Because x is what is called a bound variable. Bound variable is like a local variable, which means that in every situation, you can rename it. So this and this is literally considered to be the same syntactic formula. So by the time your brain generates the instructions to utter the word X, I will quickly rename it to Z, and then you will be wrong, right? So that's the notion, the idea of a bound variable, which I think is also explained in Egbert's book. And if you're not familiar with it, you are familiar with it at least at an informal level. However, unfortunately, I have to warn you that mathematicians are really bad with notation and bound variables. They abuse bound variables all over the place so that they don't make any sense. We are going to have to make sense of them because we have to deal with a machine. So we will be careful about them. We're still not careful enough here. I'm just warning you that we will be careful. So the way you use the turnstiles to come back here is that you indicate when a variable is available or not available. And that is how you say that it is bound. It is bound. Why do we say it is bound? We say that X is bound because it is available here. This is where the scope of X is. It's available here and nowhere else. It does not exist out here. Yes? So to give you an example of bad practice in mathematics, this is also a bound variable because you will agree with me that this and this is the same integral. So the x and the x is a bound variable. Yes. So then, if you write this, right, you committed here a horrible, horrible sin from the point of view of a computer, because the computer is going to say, what is this? This does not exist. Unknown variable x. So what would be correct is to say instead here, you don't want that. You might want to say something like, when you integrate this, you get lambda x to the third plus 3, and I still don't know what to do about this funny C business. This is also a little bit suspicious. Yes. Okay. Okay. So dependent sum. Again, we have a family. I'm not going to write everything again, but we're going to write it like this. I am using eyes. Okay, and now I'm not going to write the inference rule again. I will just say what the elements are. What are the elements of this sum? You should think of it as a disjoint union. So how do you make sure that the elements are disjoint? Well, you tag them with the index that they came from. So the elements are just going to be pairs. I, A, where I is in I, and A is in AI. Pairs. What will be the operations? So this is now this is one of the operations. It's pair forming. It is becoming a little bit suspicious that I'm using pairs, but I call it a sum. Okay, that's suspicious. It's a little bit suspicious. But anyhow, what will be the other operations? Well, there will be two projections, pi 1, and the equation will be pi 1 of a is pi 1 of ai is I, and then there will be pi 2. And you can read about this in Egbert's book, precisely how it's done. I'm hoping I don't have to go through all the details now, because I would like to explain why is this called a sum. Well, if this is called a sum, then a plus b, or the sum of two things, should be a special case, and it is a special case. So if I take my indexing set to be 0 and 1, and I take a0 to be b, and I take this to be b, I take a1 to be c, then this sum will be what? Well, not exactly, but isomorphic to b plus c. And that is the reason I want to call it a sum. Well, that was one special case. The other special case is that you take a sum of a non-dependent family. So you just sum over all i's, some set, fixed set I. What do we get? Is it I plus A? What will be its elements? The elements will be pairs, IA, where I is in I and A is in A, so that's called a product. We're going to get this, correct? Yes? Which is why, in certain literature, this thing, unfortunately, is called a product, and I think also in the Agdam library, maybe? Yeah. So some people call this product. Please don't do that, okay? You know, you should then call this function space also, right? It would be reasonable to call this function space. So you have to pick something here. So it's called a dependent sum. That is going to be a basic operation. It is omnipresent. It is everywhere, but maybe not in the form that you expect. When you say something like when you say a group, well, the type of all groups is going to be one of these things, sigma. So that will be typically when you have structures, they're described by nested sigmas. And we will come to that, and you will see that in a proof assistant, structures are so important that you actually have special notation and special names for them, like you say structure, but really, mathematically speaking, we're just talking about dependent sums. We'll do examples of this. I just want to sort of say where things go from here. So because right now we have a sigma, we have a pi, we have some operations and sets, we're using equations, but we still don't have any logic. Presumably, we're going to need logic. Otherwise, it's going to be kind of hard to do anything. So the traditional way is to first have logic and then axiomatize set theory using logic. But we are turning things around. We are starting with set theory. We renamed it to type theory. We're starting with basic constructions and operations. And I was very careful to avoid any logic. There is no or and or anything. There are just inference rules, basic inference rules. These are not logical connectives. These are inference rules, so ways of constructing things. These are recipes on how to do things. So they are more like teaching you how to use a compass to draw a circle. Okay, the rules. They are not like statements in logic. And we need logic. So where is it going to come from? So we have the idea that we're going to do logic via sets. We will make, or types, but let's call it sets. We'll stop saying sets next week. Can we get the truth values somehow expressed in terms of sets? Because truth values is what logic is about. And you say, well, yeah, maybe, because maybe we can like have a set of truth values, right? We could axiomatize this. We would say there's a set called prop, and it contains bottom, and it contains top, and so on. We could say that. And that is one way to do it. And this is not the way we're going to go. Instead, we're going to say that logic appears as a special part of sets by declaring that truth values, or also called propositions, by which I mean values like logical statements, my logic is not all sets, but sub-singletons. What is a sub-singleton? A sub-singleton is a set that contains at most one element. So for the time being, I'm going to use... So actually, I can write down what it means for something to be a sub-singleton. So a set A is a sub-singleton if the following holds. If I have A in A and B in A, then they're equal. Okay. So that is how you can say that a set has at most one element without any counting and without any case distinctions. I'm not saying empty or blah, blah, blah. I just say something very straightforward, and I say it the way an algebraist would say it. A equals B for all A and B. Like take A and B, A equals B. So that's what a sub-singleton is. Why do I want my logic to work with sub-singletons? Because there is an amazing coincidence between logical connectives and constructions. And this amazing coincidence, it's called propositions as types. Well, here I'm saying singleton, sub-singleton types, but this goes much further, so you should know the phrase. And it's a little table that you can make. And the idea is going to be the following. Suppose I have S and it's a sub-singleton. And then I'm going to say that such a set, sub-singleton, it signifies truth if it has an element. To have an element means that it's true. So what's false? It's the sub-singletons that don't have an element, namely the empty set. So the empty set for me means false. All the other singletons mean true. Why do I want so many why do I want so many things that are true? Why don't I just take one specific one? The reason I don't take one specific one is that my algebra keeps working really nicely if I take all of them. If I have just one, I will be forced to make some arbitrary choice as to which one is the one that signifies true. I'm more lucky with false because there's only one empty set. If there were many empty sets, then I would have many falses. I don't have a problem with that. Okay, so true means has an element. Has an element. There's something in it. Okay. Now let's have the amazing coincidence. So first of all, what do we have in logic? Well, in logic, we have some constants. We have a constant false. We have constant true. Mind you, this is a particular choice of a true statement. There are lots of true statements like 7 equals 7, 5 equals 5, but this is one that is considered to be canonical one. Then we have conjunction, disjunction. Well, let's do implication first. Then we have disjunction. Let's do this much first, okay? So this, as we just discussed, is the empty set, yes? This, now we do need some chosen set, a particular set, because we choose one particular statement that is considered, here I need one, so I'm just going to call it one. In fact, this is some canonically chosen singleton, so there may be a set that contains some canonical element called star. Programmers call this the unit type. This one, okay, let's think about this one. I need a set theoretic construction on sub-singletons such that, well, what are the conditions for truth? When is P and Q true? When they're both true. So I need a set theoretic constructions that says there's an element if both P and Q have an element. What would that construction be? And it also has to give you sub-singletons. It has to map sub-singletons to sub-singletons, and it has to have this property that if I give it two sub-singletons with an element, then I will get a sub-singleton with an element. But if either one of them is empty, the result should be empty. What construction is that? Product. Cartesian product does that. So conjunction is just Cartesian product. Ok? Nismo še končali.
Sorry.
You are here for?
Process, stochastic process.
Yeah, at 15 past.
15 past?
I think so, yes. This, yeah. Okay. So what about this one? This is an exercise in reviewing how many functions there are from the empty set to something and from something to the empty set and so on. But if you think about it, functions from P to Q will do the job. Because when is this false? This is false only in one case, when this is true and that's false. So that's when this one has an element and the other one doesn't. And then there is no function. And in all the other cases, you get a function. Or is very interesting, and we'll discuss it next time, because you might say union, but we don't want union, we don't have union. But then you might say, oh, how about plus? That would do, except it's not going to do, because it doesn't preserve sub-singleton. You might get two elements where you had one, but you just want, okay? So this plus is actually also a kind of very nice or, but it breaks this rule that we want sub-singletons. There are two choices here. we say, but why are we using subsingletons? Maybe there is no need. Maybe we could just use all sets, and the ones that have elements are true, and the ones that don't have elements mean false. And that is, in fact, the original propositions as types as postulated by Martin Löf. In that case, we could use this because that would be the operation. And this would now not correspond really to an OR. It's more like a decision procedure because the elements of this P plus Q, once you have an element, if it's iota 1 of something, you know that you decided that P. And if it's iota 2 of something, you know that you decided a Q. So plus is a good choice, but it breaks the subsingleton. If you want to keep it, you need another operation which will just smash everything together. So we need an operation, it's called truncation. And all this does is it takes a set and it quotients. So let me tell you what it is naively. You could also axiomatize it directly. It takes a set and it quotients it by the trivial equivalence relation, which I don't mean equality, I mean the other one, where everybody is related. So you just obliterate the distinction. So now if I give you iota 1, you don't actually know whether I meant iota 1 or iota 2 because they're equivalent. So I will actually give you a whole equivalence class. So this equivalence class will contain both iota 1s and iota 2s, so you don't know anymore. Okay? That's what's going to work. And we're going to come back to this again later on. I just want to give you a kind of a preview because it's going to be probably also in the books. So what will be for all? I have a family of singletons, and now I want to create a new singleton such that this singleton is inhabited has an element if and only if all of them did. A little bit of thinking will reveal that it's this. Product is for all. Let's think about it. If one of them is, so let's think about when this is false. If one of the p of x's is false, then the whole thing is false. If one of these p x's is empty, then you can't have a choice function. So it will match. And the last one, so let me finish for today. The last one here is existential. There is one more, which we will do next time, which we don't know right now. But this one, you have the same dilemma as with OR. You say, hey, we could use sums, but this will break the rule that you need a singleton, a subsingleton, because you might have many. And now the difference between smashing them all together into a singleton set or not smashing them all together, the difference is the one between what exists in mathematical practice, but you were never told that it is a thing, because you were only taught the smashed thing, namely the existential. It is the difference between a concrete existence and abstract existence. In mathematics, sometimes you construct a specific thing that you later refer to, and that's when you don't smash, when you have a sigma, because the specific thing you constructed is the first component, is this component here. I construct a specific x such that it satisfies some desired property p of x. And if I truncate, that is like not telling you which x. Yes. And you will observe in mathematical practice that even though mathematicians write theorems that say there exists blah, 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 what they will actually do is in the proof, they will construct a specific thing. And then you can see that they did not mean exists, because later on they will use the thing they constructed in the proof. But then it couldn't be exists, because exists does not work like that. When you prove that something exists, you don't have a specific thing in mind. You forget which one it was. So if you don't forget, that means it's this thing without the smashing business. And these are two possible choices on how to formalize things. That's why I'm talking about it. When we come to formalization, we will have to be honest. So when you see in the book an existence statement, you will have to think, wait, they might be tricking me with this logic business here. Maybe they wrote exists, but they really went for a construction. So I should not be doing an exists. I should be constructing things. So this is an important point of formalization, where you see the discrepancy between what people do and what people say. And there will be more examples like that. Okay, finished. Too late for today. Homework, install Lean. And read more about type theory, please. And get on Discord. 3 homeworks. 3. This is like the Spanish Inquisition. So 1 homework, 2, 3. Okay, so Lean, Discord, and read a little bit about type theory. The first 4 chapters are just 35 pages, I think, so it's not that bad.